Can you all hear me okay?
Yeah.
Okay. So next week's meeting is optional. What I'm going to do is have the 8 o'clock group meet at with you guys. So I'm going to give them the Zoom link so that they can join you and ask whatever questions you may have, either in the lab or whatever. Okay. Just for last minute questions on the lab. So what I'm going to talk up today is I want to talk about the lab and review where I left off the other day in lecture. I finished off in lecture the other day talking about the RLC circuit. So basically, it's just a circuit with a resistor, capacitor, and inductor. And really everything that we've learned so far in this chapter is contained within this circuit. And what I said was, okay, to analyze this circuit, all we need to do is draw a phasor diagram. We could solve a differential equation and obtain the same results, but sometimes the math obscures things. And we could focus more on the physics. And if I have time, and I had a little bit of time with the other group, at the end of class, I will set up the second order differential equation and go through it briefly. But if you go to the modules, I have it fully worked out in a video in great details. And the video in the modules, there's several videos in the modules for this lab. You got to watch them. Okay, so you might be asked a question on the exam. All right, so I really need you to watch them. Okay, it'll also help you understand the lab too. So this circuit, so one of the things I said is we can draw a phasor diagram to understand the behavior of the circuit. And so there's really not a lot, if you think about it, there's not really a lot involved in drawing this picture using the phasors. I just need to recognize that since these three are in series, the current through each one of them will be the same. But the voltages will be different. So my figure will involve phasors, vectors, or arrows involving voltages. But I want to start with the current because I know that the current through the circuit and the voltage across the resistor are in phase. And so let me draw a phasor for the current. This is I sub m. I'm going to leave the subscript on this because there's a resistor, an inductor, and a capacitor. There's so many subscripts. I'm just going to be write I. That's basically this guy. It's the maximum current in the circuit. And the RMS would be this times the square root of 2. Since I know the voltage across the resistor is in phase with the current, then I can draw the phasor. It's in phase, that means they're parallel to each other. So far, so good. Now I just got to do the inductor. Of course, the current through the inductor is the same, because they're in series. But we know that the current in the inductor lags the voltage by 90 degrees. That means the voltage is ahead of the current by 90 degrees. And so all I got to do, I'm going to just draw it of arbitrary length. Like that. And then I know the current, the current leads the voltage across the capacitor by 90 degrees. And so then I will draw V sub C. By the way, I arbitrarily draw this to be longer than this so I can write everything in the first quadrant. It doesn't have to, I mean, it's possible this could be longer, V sub C can be longer than V sub L, but I'm just doing it because I want to draw everything in the first quadrant, okay? And so the next thing I'm going to do is, since these two are 180 degrees out of phase and they're vectors, I treat them like vectors. And the difference between the two, and I'm going to draw this very dark. I know this is a bad color. I'll write the words in black, or the letters in black. This is V sub L minus V sub C. I have two vectors that are perpendicular to each other. I use the Pythagorean theorem to find the length of a vector. And there's the phase angle. That's the phase difference between the voltage from the power supply and the voltage across the resistor. And I'm going to show you that phase difference in a minute. I'm going to show it to you what that means in a circuit, okay? Because you're not going to be able to observe this with your scopes. I have a scope where I can observe the voltage across the resistor and the voltage from the power supply at the same time. You can't do that. So you can't see the difference in phase. Okay, so I'll do that in a minute. And then from this triangle, this right triangle, it's called the impedance triangle, I can figure out everything about the circuit. I just use trigonometry. Now the tangent of this angle is basically this over this. But of course, this has current in common. So when I take this and divide it by that, the current cancels. That's why I wrote tangent of phi is x sub L minus x sub C over R. And then the sine of phi is opposite over hypotenuse, which is going to be this guy divided by what z is. And then cosine of phi is R over z. Again, the i's cancel. I can also write as v sub r over v sub m. That's cosine of phi. It's either one. Okay. So if I wanted to, I can write it like this. I don't have enough space to write that one. Okay. Questions so far about where this comes from? Are we okay?
Is the Z just a letter, just like a constant, or
It's
what
this.
does Z represent?
Z represents this thing.
Oh, okay.
Okay, that's the total impedance of the circuit, right? I mean, and I wrote it here just so. So it's the total impedance of the circuit. Okay, so it would be the hypotenuse. And so you can derive this very easily because if you use the Pythagorean theorem here, V sub m is the square root of V sub r squared plus V sub L minus V sub C squared. But this is current times resistance squared. This is current times x sub L. And this is current times x sub C. And it's pretty obvious that I can factor out the I from everywhere. And when I factor out the I from everywhere, I get this thing. And so this is like the effective resistance of my circuit. It's called the impedance. Because this thing depends on frequency. Right? This denominator is frequency dependent because x sub L and x sub C are given by these expressions. Are we okay with that? Now.
Yeah.
Okay. So Couple things you have to understand. This is different from DC circuits, and this is, students get confused on this. Suppose that the voltage across the inductor, I measured at 30 volts. And this voltage, I measured it to be 20 volts. And they took a multimeter and they put it across these two. So in other words, I want to find the voltage between this point and this point. What's the multimeter going to tell me? How would I know? Is it 50? What do you, anybody want to guess? What's the voltage going to be between this point and this point? If this is 30 and this is 20.
I feel like it's a trick question.
Well, I mean, what do you think though? What would you intuitively say?
Is it 10?
Yeah, it's 10. Why do you say 10?
Because it would be the inductor minus the voltage of the capacitor.
Yeah, these two are 180 degrees out of phase. Right? So you actually have to subtract them. Because without thinking about it, you would say 50, but it's not 50, it's the difference between these two. Okay? Now, that's how they work because they're not in phase. Really what you're doing, if you think about it, you're adding sine functions, right? You're adding this to this. These are RMS values, or these are maximum values. But if you're looking at it, I mean, if you're really looking at how these work, I mean, I didn't draw them very well. If they're 180 degrees out of phase, then they would look like this. And so the total voltage would be the difference really between this peak and this peak. So what about if instead of this, let's say this was 40 volts. And I wanted to measure this voltage. I mean, and this, again, it's not a trick question, but it's based on looking at that picture. Okay, if this is 40 volts, the voltage across here, and this is 30 volts, what's the voltage between these 2 points? It ain't 70. Again, this is not a DC circuit.
Would it be the Pythagorean theorem between the two vectors?
Yeah. So this is 30, that's 40. It's a 3, 4, 5 triangle, right? So that'd be 50 volts. The multimeter would say 50 volts. Okay. This is why this picture is so important, because this tells you everything. Okay. This tells you everything you need to know about the circuit. Okay. It's way different from DC circuits. If this was a DC circuit, yeah, this would be 70 volts. But that's not what happens here, because these voltages are 90 degrees apart. Okay, so you just can't add them. We got to add them like vectors. We can't add them like numbers. Okay. And so that's one of the big things that students have a difficulty with here is they learn something a certain way earlier, but this is completely different just because they're not in phase. Okay, when you do DC circuits, everything's in phase, essentially. Okay. Are we okay with that? So, the question is, and I have a question here, when is I a maximum? So let's write the equation for I up here. Um, at what frequency is I maximum? Of course, if you were in calculus class, what would you do to figure that out? You would take the derivative of that function with respect to omega and set it equal to 0. But we don't need to do that because it should be pretty obvious. If these are the only two terms that depend on frequency, r is a constant, then when this term in parentheses is 0, that function is maximized. Isn't that true? This is maximized when it's maximized when x sub L equals x sub C. When omega times L equals 1 over omega C. And at this frequency, I'm going to give it a special notation. I'm going to call it omega naught. And I get omega naught squared is 1 over LC. And omega naught is 1 over the square root of LC. That means the frequency then is 1 over 2 pi times 1 over the square root of LC. This is called a resonance frequency. This is when you get the maximum energy transferred from the power supply to the load. Okay? This is when you get the maximum energy transfer from the power supply to the load. This is the frequency at which the system wants to oscillate at. This is called essentially the natural frequency of oscillation. Just like if you take a mass on a spring and you just start moving your hand up and down, there will be a rate in which you move your hand up and down in which the oscillations of the mass on the spring get bigger and bigger and bigger. That's that natural frequency of oscillation. That's called a resonance frequency. So this, you'll see this in the 215, except that it has to do with, you'll see it applied to the mass on the spring problem. Okay. So it is at this frequency that energy transfer is a maximum to the load. Okay. Questions on this? So anytime I denote omega naught or F naught, I'm talking about the resonance frequency. What happens to the phase at the resonance? What happens to the phase between the power supply voltage and the voltage across the resistor? When these two are equal. Isn't it 0? If these two are equal, the difference is 0. Tangent of 0 is 0. Tangent of 0 is 0. So the phase difference between the two is 0. So what does that mean? Physically, what does that mean? If I wanted to see the effect, if I had a circuit, what would I be seeing when I talk about the phase difference being different? What does that mean? What does phase difference mean? It's one thing students have a hard time with. The phase difference is the difference, really an angle, in which these peaks occur. That's what the phase difference is. If you plotted this as a function of angle, the phase difference is the difference in where the peaks occur in angle. So let me show you an LRC circuit that I put together. It's a little bit different from the circuit you're using, and I'm using better equipment than you are using. Okay. My 10 millihenry inductor has a much lower resistance than yours. So the quality of my circuit is going to be much better. Okay, let me change to the camera. So I put together an RLC circuit. My inductor is 10 millihenries, but the resistance of the inductor is lower than yours. I mean, mine's much lower. My power supply is way better than what we're using for the lab. Okay, I can drive more current, so I'm not going to have the issues that you're going to have. And so the resonance frequency, if I plot I versus omega, it would be it's a very narrow peak. So let me change the scale, just give you an idea. Hold on a second. What you're looking at is the voltage from the power supply, which is yellow, and it's about 1 volt peak to peak. No, I'm sorry, 1 volt in amplitude. So 2 volts peak to peak. And then the orange is the voltage across the resistor. And I have my signal generator set to 560 hertz, which in my case, because I have a different capacitor than what you're using. In my case, the resonance frequency is 560 hertz. Notice that the peaks come at about the same point in the sine function. Let me do this. Can you see that the peaks occur at about the same angle? Is that clear to you, folks?
Yeah.
Okay, so what I'm going to do now, I'm going to actually I'm going to lower the frequency. Let me stretch this out. I'm going to lower the frequency, and I'm going to you're going to see what happens to the phase shift. The other problem is the voltage across the resistor decreases. Hold on a second. I got to change a couple things. So now I'm down to 100 hertz, and I got to change things again. Can you see the phase shift is significantly different? The peaks don't come at the same time, right? Do they? We're not. The phase shift is getting close to 90 degrees, in fact. So let me go the other way. Let me go at higher frequencies. I'm going to go to about 1100 hertz. And let me change again. As I increase the frequency, the phase shift gets bigger and bigger and bigger. I'm at about 2700 hertz, and you see the phase shift is, the peaks are getting further and further apart. Do you all see that? So that's what happens in the circuit when we talk about the phase shift. The peaks get further and further apart. Now, if we were doing this lab on campus, or if you had this scope, you'd be measuring the phase shift between the power supply voltage and the voltage across the resistor. But you don't have that luxury, which is actually means you're collecting less data. Okay, your table would have at least 2 more columns in your lab if we were doing this on campus. So, like next fall, we're doing this on this lab on campus. So, this poor students are going to have to add 2 more columns to their data table. Any questions on what you observed? It's too bad you don't see the power supply. The power supply is like way back here. It's a nice signal generator, but that, yours costs $30. The one I'm using costs $500. No questions, concerns? Okay. I'm going to bring up another thing regarding. Oops, sorry about that. The RLC circuit. So, when the current's maximized, in other words, when you're at this frequency, when the current's maximized, guess what else is maximized? The voltage across the resistor. So at the resonance frequency, the voltage across the resistor is maximized because the voltage across the resistor is just going to be this times R. But the voltage across the capacitor and the voltage across the inductor is not maximized at this frequency. It happens somewhere else. How do I figure that out? Well, the voltage across the inductor is going to be this times the inductance. I'm sorry, this times the reactance. How do I figure out the frequency in which the voltage across the inductor is maximized? Well, then I have to do some work. I got to write the expression for the voltage across the inductor and then take the derivative of the expression with respect to omega and set it equal to 0, solve for omega. If I'm doing the capacitor, then I'm going to take this, multiply by x sub c. That'll give me the equation for the voltage across the capacitor. And then take the derivative of the expression with respect to omega and set it equal to 0. Solve for omega. And since I know omega is 2 pi times the frequency, I can solve for f. So and I'm telling you this because one of your homework problems, you have to do this. Okay, I just told you how to solve one of your homework problems. Okay. Questions? Everything going okay then? No concerns? All right. I'm trying to find my eraser. Here we go. I want to rewrite this expression for you. Because normally we don't work with the expression in this manner. Let me put in the omegas. Oops, I forgot to pin myself. Okay. Let me write everything in terms of omega. And I'm going to pull out an L from this term. So let me put out L. I'll get the following. But L times C is omega squared. Oops. I'm one step ahead of myself. Okay, so the next step I'm going to do is, and I'm not going to rewrite the next equation. I'm going to pull this guy out. So I'm going to pull this guy out. Sorry. I'm going to get that. And then I'm going to pull this thing completely out of the radical. And I'm going to get the following. This is the expression for your current in your circuit in the lab you're doing as a function of frequency. Well, angular frequency. Okay. You're going to plot I here and omega here. I know you're collecting it as a function of f, but you want to plot it in terms of the angular frequency, because it's going to be easier to do the curve fit. Because if you plot it as a function of f, then you're going to have a bunch of 2 pi's everywhere, which is going to make things a pain. The graph kind of looks like this. How wide this is, or how narrow this peak is, depends on the value of the resistor. If the resistor is lower, this is really narrow. If you took 215, and you didn't do this lab this semester. There's a lab you do in 215 where you actually do a curve fit to something that looks like this with a mass on a spring, but I think in 215 they don't do that. Because we're online, you can't do that lab. So never mind. You're going to do a curve fit to this equation. You're collecting this data. Now granted, in the lab that you're doing, you're not really collecting the peak voltage, the peak current, you're collecting the RMS, but who cares, because that's just this thing times 1 over square root of 2. Okay, that just scales the peak down, who cares? Okay, the shape is still the same. So you're going to do a curve fit, and you're going to do it either in graphical analysis or side Davis. Either one. It'll work in either one. It'll take, actually, graphical analysis will take longer to do the curve fit. So you have to actually define this function in graphical analysis and side Davis. They do not have this function built in. This will be your variable. And your curve fitting parameters will be V sub m, R, and omega naught. If you want to, you can make that a curve fitting parameter, but I don't know, having a fourth one might cause a problem. I mean, it's asking a lot of graphical analysis. Side Davis probably could be able to handle it. Okay, so you're going to measure this value in the lab, so you can use that value in the lab. Of course, that value is going to be bigger than what it should be, because the resistance of the inductor is like 25 ohms. So your L value that you're going to get from the lab is going to be higher than really what it should be. Okay. So you're going to use these as your curve fitting parameter. You want to determine this. This will give you the effective resistance of your whole circuit. This is probably not going to be a great value because your darn signal generator is current limited. We're going to be really at the, we're going to be pushing the power supply in this experiment. And so this value is going to really might not make sense to you in this, this value might not make sense to you in this lab. But we'll just go with it. We're, just because of the fact that we're limited in terms of the equipment we have. And this will be just D sub M. Okay. This would be the RMS voltage. But the interesting terms are these guys. In fact, this is the one I'm most interested in because it's gonna tell us what the resonance frequency is. It's gonna be the peak in the current. And we're going to extract information from it. We're gonna look at something called the quality of the circuit. The quality of the circuit is defined as 2 pi times the maximum energy in the cycle divided by the energy loss per cycle. And it turns out to be omega naught L over R. You're going to calculate Q along with the uncertainty. You're going to get, you have this value, you know its value in the uncertainty, you know this value in the uncertainty, and you know R in the uncertainty. You can calculate Q along with the uncertainty. But there's another way to determine Q. And I'm not going to prove it here, but I have a video. It's like a 10-minute video in your module. You have to watch it. And it proves that this is equal to the square root of 3 times the resonant frequency over delta omega. Now what's delta omega? Delta omega is called the full width at half maximum. It's the two frequencies. It's the difference in the two frequencies in which you get half the peak. So if this is the peak current, this is half the peak. The peak occurs at one frequency, half the peak occurs at two frequencies. And the difference between the two is delta omega. This is called the full width at half maximum. And so you're going to actually, by I, you're going to determine this value and this value. Calculate delta omega. So you're going to calculate your Q this way and just compare the results. And see if they agree, if the values overlap, including the uncertainties. Now what does your Q represent? Really your Q represents how wide or how narrow this is. The higher your Q value, the narrower the peak. Why is that important? Well, let's say you're tuning to a radio station, and when your tuner is an RLC, has an RLC circuit in it. You're tuning your RLC circuit to a resonance frequency. Do you want your Q to be high or do you want your Q to be low on your radio? In other words, do you want your graph of I versus omega to look like that? Or do you want it to look like this? This is low Q, that's high Q. Which one do you want for your radio? Remember, you're picking out a frequency.
I would say the top one.
So if you choose the top one, this is a low Q, that means that when you tune your circuit, you're picking out a whole bunch of frequencies. Because your tuner picks out the frequency in which you want to hear, the frequency of the radio station, right?
Yeah.
So don't you want to pick one? Don't you want your circuit to just pick one frequency?
Yeah.
Right. You don't want it to pick 96.9 and 93.7 at the same time, because what are you going to listen to? It's going to sound like noise, right?
Yeah.
So what you want is, you want your graph to be really narrow, so you want high Q. Because if it's too wide, you're going to pick up several stations at the same time, which happens, right? I mean, you've tuned the radio and you put it on the station and you can hear two stations. And in fact, sometimes what you'll do is you'll tune it and you'll move the dial, and you'll notice that you can still pick it up even though you've changed the frequency quite a bit. But really what you want is to be narrow. So you can pick up that single station. You can pick out a single frequency and not a whole bunch of them. And engineers, electrical engineers, this is important when they're looking at tuning circuits. Okay, designing the circuit so their Q is high if they're tuning to something. And so you're gonna analyze your circuit in terms of the Q value. So you're going to make this graph. You're going to make a curve fit. I prefer that you use these as your fitting parameters. If you want to use a fourth one and you want to try it, go for it. Okay. And this is where the more data points you have, the better it is. In fact, for this lab, there's a lab like this in Physics 215, but you can't collect as many data points because the lab is extremely time consuming, more time consuming than this one. They can only get like 10 data points, but it's much harder to do the curve fit. For us, it's easier because you have a lot more data points. Okay, so the more data points you have, especially around the peak, and then you want to have some here and some out here, the better it is for you. Okay. Questions? So let me show you the file for the lab. Let me go to the last page. This last page shows you everything you have to graph. 3 graphs, but there's 6 plots. The graph in the upper right-hand corner is the one I was just talking about. And you really should plot as a function of omega. This graph, this is an old figure. This is probably like 25-year-old figure. But you want to plot as a function of omega, not frequency, because it's easier to do the curve fit. Okay. The other ones, if you want to plot them as frequency, that's fine. The bottom graph, you just got to plot on the same graph the voltage across the capacitor and the voltage across the inductor as a function of omega or F. And just look at what happens at high frequencies and look at low frequencies. Don't need to do a curve fit unless you like doing curve fits. Okay? Because you're only going to look at tendencies in that graph. You're going to write a figure caption explaining what the tendencies are. And then the first one in the upper left-hand corner, you're going to be plotting the impedance, the capacitive reactance, and the inductive reactance as a function of frequency based on your measurements. And you're going to use that graph to find the resonance frequency by eye. You're not going to do a curve fit. The bottom of the Z graph is the resonance frequency because if we look at this expression, Z is this expression. Z is minimized when X sub L equals X sub C. Z is minimized because the current's maximized. Okay? And that's going to allow you to find the resonance frequency. And this should coincide with when X sub L and X sub C are equal. When the graph for X sub L and the graph for X sub C, they cross. Okay? You don't need to do a curve fit on that one either. You only need to do one curve fit for this lab. So I have 3 videos. One shows you where actually, hold on a second. One shows you where this equation comes from. And that square root of 3 is important because the square root of 3 is there because I'm plotting I versus omega. If I was plotting power versus omega, that square root of 3 wouldn't be there. But because I'm plotting I versus omega, that square root of 3 is there. That's only there because I'm plotting I versus omega, not P versus omega. If I plotted P versus omega, this thing wouldn't be there. So I have a video that talks about that. I have a video that talks about what Q is. And then I have a video where I actually derive this in what's called the time domain. So everything that we're doing here, everything that we've analyzed here is in terms of frequency. And so we call this the analysis in the frequency domain. But I'm going to do one in the time domain. And what does that mean? I'm going to actually solve for Q as a function of time. I'm going to solve the second order differential equation. And I have a video where I lay that out in complete details. So I expect you to watch that. Okay, there's a set of videos in the module for this lab. I want you to watch that. Okay. So let's go to the data table. You're going to have to add some rows in this data table. I didn't want to add them all in. You're going to have about 25 to 30 rows. And I didn't mention this to the other group. So let me add some rows. What's bad about this table?
That's not on one page.
Yeah, isn't that annoying to have it on 2 pages?
It also doesn't have a caption, if that matters.
You're right about that, and you're right. It should have a. It doesn't say table 1 or what, does it? That's
No.
my bad. but the thing is, yeah, I mean, actually, you do have to enter everything manually, but I mean that's kind of a given. But I do want the table to be on 1 page. It should have a caption on it. Usually, I do that. Oh, there it is. Table 1 impedance is a function of frequency. I mean, it's right there. So, but I would put. Oops. I would place this on 1 page. Okay, so then I can add the rows, etc. But you're going to collect. You're going to enter the value for the frequency. V sub L, V sub C, and I, because you're going to make those measurements. But then everything else you have to calculate. You have to calculate omega, you have to calculate X sub L, X sub C, and Z. Now, what's the best way to do this? Yeah, it doesn't do the calculations for you, so what should you do? I'm going to do this. I'm going to hit copy. Yeah, I'm going to actually do this in Excel. I'm going to hit copy. And let me go to Excel. Hold on, I got to change things for you guys. Excel. Let me open up a different sheet. And let me paste my table here. I'm sorry, what do you mean, Jacob, doing an insert? This table, I didn't make this table so that it's, yeah, I guess you can. I haven't thought about that. If you want to do that, that's fine. I guess I'm just doing it the old-fashioned way. Okay, that's fine. Yeah, I guess you can. I never thought about it. You can insert it from you can insert it from here. I've never done that one before. Anyway, let me just talk about one of the things about doing this is I can save this file. I can I can save this Excel spreadsheet. So some people had problems with my spreadsheet from the last lab, and I think it's because because it was from something I created. But let me just enter some numbers. Okay, I want to calculate omega. So to calculate omega, let me make this bigger so you can see better. Hold on a second. And I don't know how familiar everybody is with doing the calculation. I'm going to hit the equal sign. I hit 2 star. The pi function looks like this. And then start a cell. I'm going to multiply by the cell number, A3. That gives me the value. Then I'm going to just go in the bottom right-hand corner, click and drag. What's the problem so far?
Sig figs.
Yeah, that's terrible, right? Excel doesn't know the rules for sig figs. Let's pretend we know the frequency to the ones place, which is the case because we can adjust the frequency by 1 hertz at a time. And so these values should be 3 sig figs. So I'm going to go to Format, Cells, Number. I'm going to write them so they're 3 sig figs, which in this case is 1 decimal place. In this one, it'll be 2 decimal places. Two. So now they're all 3 sig figs. Let's say I measured Visabel. I want to fill out a whole bunch of data. Okay, so then let's say I measured I. And I want to calculate Xabel. Like equal. I put the cell value. Xabel is the voltage over the current. So I'm going to take C3 and divide it by E3. And then I'm going to just click and drag. And then at the bottom here, I can hit equal average F3 colon F6. And of course, you can fix the sig figs right at the end, and then I can get the standard deviation. Actually, if I want to get the uncertainty, I can do this. So let's look at the standard deviation. Standard deviation is F3 colon F6 5. And I'm going to divide by square root 3. Another way to do it is this. This tells me the number of cells that I have filled. And so the count feature counts the number of cells that have a number in it. So you have to count how many cells. Okay, so that's one thing you do. And I forgot to show that to the other group, but. Are we okay? You guys okay with doing the calculations in Excel? then you can, unless you've inserted the Excel table already in Word, you can actually take this, save it, and then copy and paste it into Word, however you want to do it. But just be careful with the sig figs, okay? And watch the units in some of these millihenries and microfarads. Just be careful, okay? Make sure that things make sense. And then, because you're going to find, you're actually going to do, for L, you're going to calculate the average and uncertainty. For C, you're going to calculate the average and uncertainty. Okay? Questions, concerns? We're okay? Okay, everybody's quiet. So, all right. What I'm going to do now, sometimes, what would the sig figs be for which one? Since you are starting at 200. You're talking about the current or for frequency? Well, it's to the ones place. So if you're below 1,000, then it would be 3, right? If you're below 100, it would be 2. And if you're above 1,000, that'd be 4, right? Because if you know it to the ones place. Right, the number of sig figs, I don't tell you the number of sig figs you have. The measurement tells you that. So it's how big the measurement is and then how precise the measurement is. That's just like a ruler. A ruler will give you 1, 2, 3, 4, or 5 sig figs, right? Same idea. It just depends on the precision and the quantity, the size of the quantity you're measuring. So for frequency, it's going to vary. Because you're going to go over 1,000 hertz. So you're going to have four sig figs for stuff over 1,000 hertz. And 3 sig figs for stuff below 1,000 hertz. Okay? All right. So what I'm going to do now is take a look at the RLC circuit in a different fashion. I'm going to set up the differential equation. Actually, I shouldn't erase this. I'm going to leave it there. Hold on a second, I messed that up. I was trying to do it to get more space, but let me leave that there. Okay. All right, so I want to set up the differential equation for the RLC circuit. I'm going to apply Kirchhoff's laws. I have a power supply, a resistor, capacitor, and inductor. So that means that I have V sub m cosine omega t minus I times R. Actually, I'm going to write it R times I. You'll see why in a minute. Minus Q over C minus L di over dt equals 0. This is Kirchhoff's law. Okay? I set up the different, I'm setting this up. What I want to do is solve this. I can set myself up to either solve for Q or to solve for I. I'm going to solve for Q. Okay? Last week I solved for I because it was more convenient for me to do that. Okay? I is dq dt, right? So I can rewrite this. And really, this is the second derivative of Q with respect to time. Let me divide both sides by L. This is called an inhomogeneous second-order differential equation with constant coefficients. That's what the mathematicians would call it. I just call it just a second-order differential equation. Okay. When you solve this, there's actually two solutions to this thing. The total solution for Q as a function of time has two parts. One's called a complementary solution, and the other one's called a particular solution. It turns out that this is a transient solution. This is what I got last week. This is the case for when this is 0. Whether this is 0 or not, this will still solve that equation. Plugging the transient solution that we talked about last week into here will still work. Okay? And that's because when you operate on these guys, you get 0. And this solution is called a steady state. That's the one I'm interested in. And when you saw the RLC circuit on the scope, you never even saw this. This dies out quick. Okay? This dies out very quickly. You don't even see that. Those of you who take 215, if you do a driven down harmonic oscillator, it takes forever for it to go away. Okay. But the steady state current, the steady state case, you see right away. And I'm interested in this. Okay. Right now, I'm not interested in the total solution. I did this last week. I'm interested in this part. Okay. So I'm interested in a particular solution. I'm looking at the case when the transient part is gone. So I know that my current, from our experience, I know that my current depends sinusoidally on time. So I'm going to guess that Q sub P is going to be this function. This is my phase shift. I'm just using delta here. Why am I using sine instead of cosine? Because when I take the derivative of the sine function, I'm going to get the current. That's going to be the cosine function. Okay? And so I'm going to take this and stick it everywhere up there. So I'm going to do V sub m over L cosine omega t minus r over L. What's the time derivative of Q? What is that going to give me? What's the derivative of sine? Then this term is going to give me but what's 1 over LC? Isn't that the same as omega naught squared? So can I just put A times omega naught squared? And then the last term, if I differentiate twice, I'm going to get the same function again. Let me collect these two terms. And then write the rest out. So far, so good. I'm going to make it worse now. I'm going to expand this term, and I'm going to expand this term. So here we go. This is the fun part. Sine, sine, right? Sine, no, sine, cosine, sine, cosine. And this is cosine, cosine, sine, sine, with a plus in between. This whole thing equals 0. I don't want to write it on my wall, okay? So now what I'm going to do is I'm going to collect these terms together. So I'm going to collect those terms together. So sine of omega t, and I got to write kind of small. And then the other term with the sine omega t is this one. And then I'm going to collect all the other terms together. I'm going to collect this one, and that one. So this is going to give me then I have, what do I have here? I have this one. I probably should have pulled out an A from everything to make things a little bit easier. Okay. This mess has to be 0 independent of t. What must be true about the terms in the brackets? If this is always true, independent of time, the terms in the brackets must always be 0. So this thing in red has to be 0. This thing in blue has to be 0. That has to be true. Okay? Because this expression has to be true, has to be equal to 0, independent of the value of time. So let's set this equal to 0, which means that this term equals this term. The a's cancel. And what you get is tangent of delta is omega squared minus omega naught squared. But if I bring this upstairs, and then I cancel out one of the omegas, what's omega naught again? Omega naught is omega naught squared is 1 over LC. And so this is that. Okay, so you can see where the solution comes from. So the next thing then is to solve this term, this guy. Does everyone see this? So because this is true, then sine of delta has to be equal to and cosine of delta I forgot the L here. And I'm running out of space. So then once I know this is what I verify this, the next thing is to get what A is. Well, if I set this equal to 0, that means this term is equal to all this stuff. And I can factor out the A. So then A ends up being B sub M over L. So then I got to substitute this over here and this over here. And what I get is this. Hopefully you can see this. And if you put this up here and then take the time derivative and do some algebra, I don't have time right now, then you will get that expression. Of course, that's a lot more work than what we did. We derived our equation for I much faster. And so in doing it this way, it kind of hides some of the physics, but it works. Okay, and I did a video on this. It's in the modules, and I went through all the details. Okay. The only detail I didn't leave was me plugging this into here because I don't have space on my board. And in the step in going from here to here, I don't do that in the video just because I don't have that board space. But you guys should be able to do that. Questions, concerns?
I have a question real quick.
Sure.
So these videos that you're talking about, the only ones that I see in lab and in a class are just electroboom ones.
In the modules?
Yeah.
Hold on, maybe I didn't transfer it to our, hold on a second. I thought I transferred it to ours. Because I created it for the other class and then, it didn't transfer. I'll transfer, I'll copy it into this one.
Okay, awesome, thank you.
Okay, for some reason it didn't, For some reason it didn't copy, I don't know why.
So these videos that you're referring to, they'll be in the lab module, right?
They'll be in the lab module.
Awesome.
Yeah. And for some reason I guess I didn't copy it. I thought I did copy it into this course. Like I'm doing it right now as we speak. Because I don't want to forget. Okay, let me see if it's there now. Sorry about that. I didn't copy it, that's weird. Oh, there it is, it's there now, okay. So you'll see it now. Other questions? Okay, so I'll see you all at 2 o'clock then.
Thank you, Professor.
Sure, no problem.
Thanks.
You're welcome.